Good morning. I'd like to say thank you to MSC for inviting Intel to be a part of this webinar. And I'd like to take this opportunity basically to give you a brief overview of the underlying hardware and software advances at Intel that can allow you as an end customer to benefit from MSC's latest software releases. My key message is that it may be worth it to you as a mechanical engineer and user of MSC software to understand a little bit more about hardware and software architecture than in previous years so that you can make the best decisions to increase your engineering productivity in a knowledgeable way. For instance, one of the things that we're seeing right now in terms of the way that development has gone over the last few years is that about 2 years prior to a product launch of a new architecture, Intel has defined and announced new vector extensions, abbreviated advanced vector extensions is abbreviated as AVX, and we add those new instructions to our existing list of legacy x86 instructions. And then our software teams update our compilers to handle those new instructions as the hardware teams are developing their new processor features. Then next, our math kernel library, or MKL team, compiles and then optimizes the type of mathematical functions that MSC uses in their software products. So then those compilers and libraries are tested on pre-release hardware as it becomes available, so that we have significant experience with all the technology prior to release. When the product is actually released, such as September 8th, we released our new E5 2600 V3 series. The existing compilers and math libraries have all been tuned and are ready to go so that MSC can just compile and relink existing code with those compilers and libraries to give you a more productive, faster end-user experience on existing or on the new hardware. So I have to go through a few legalese slides here. Generally, they just say that we've reserved the right to do work to optimize software on our hardware. So the key advances in hardware that I'd like to just mention today is the new Haswell lineup, the otherwise known as the E5 2600 V3 processor family, as well as the coprocessors, the current Xeon Phi, and then I'll just mention a couple things about our next-gen KNL, our Knight's Landing product. And then I'd also just like to mention a few things about our storage solutions. So the general trends, of course, are to smaller line width processes. We're working on 14 nanometer processes to release our next line of consumer and then server processors. And generally, rather than increasing clock, we're adding more cores and better cores, and each of those cores has longer vectors, longer vector instructions. In other words, instead of just doing A times B, they can do 8 multiplications of A sub 0, A sub 1, A sub 2, up to A sub 7 times B, and so on. And so one of the key instructions that we just released is our new fuse, multiply, and add. So, and then in the software world, as I said, we have to keep all the software that we provide up to date with the hardware, and so we now have the V15 compilers with OpenMP4 support. And one of the nice features of the new compilers is that we get much better vectorization for Fortran C, C++, and much better vectorization reports for anyone who actually does software development. So this can help Robert and Travis, for instance, in the daily process of looking through the code and optimizing it so it runs best on our hardware. Some of the new MKL features are the cluster support for MKL Pardeso, and then there's automated offload of selected BLAS Level 3 functions for the Xeon Phi. Intel also makes a wide variety of optimization tools V-Tune amplifier. We have two new products, Advisor and Inspector, that can be used to, for instance, to look for memory leaks or race conditions. And then we also have Intel Trace Analyzer and Collector for MPI codes that do distributed multiprocessing. There's also Intel MPI. And then if you use Xeon Phi, there's another package known as Intel MPSS. And then in addition, we also have a TBB, which is our threading building blocks. These are open source as well as commercially supported functions. And then in addition, we have the integrated performance primitives. Now all of this comes with the package now known as Intel Parallel Studio XE Cluster Edition. So that's the key new product. So with all these changes that we've made over time, since I've been working for Intel, I joined in 2005, we've seen a 22x performance increase for spec int rate, spec CPU 2006, the integer rate version, and the so the culmination right now is shown here is 18 cores per socket at 2.3 gigahertz. In addition, we've also improved our energy efficiency so that the performance per watt has gone up by a factor of 27. So, oh boy. Well, there's supposed to be an equation there, but I can't see anything. The key thing is people know Amdahl's law. So there's an Amdahl's law as you parallelize across a set of cores on a chip, but there's also Amdahl's law applies to SIMD parallelization within a vector unit, for instance, that does, say, 8 floating point multiplications at the same time as what it would take to do just a single multiplication. So in general, the speed up for, the number of cores has gone in that time frame of that previous chart from 2 cores to 4 cores in 2006 for a server, and now we're at 36 cores as our maximum in 2014. And that's just for a 2-socket box. The 4-socket systems have even higher core counts. And the typical vector length for the number of actual values that you can operate on at the same time, it could be 1, 2, 4, 8, even all the way up to 16. So the goal, of course, is to reduce the serial fraction that does not execute across the cores, and then reduce the scalar fraction of the code that does not use the vector unit. And if you do all that, your vector speed up will be the number of cores times the vector length. And so that's where a lot of the that's where that 22x has been coming from all the changes that that have gone on at the hardware level. So now the latest E5 2600 V3, or formerly known as Haswell, this is a block diagram showing the a new socket. And so, for instance, the things that are new are highlighted in yellow, and the existing features that are similar to previous generations are shown in blue. One of the key things here is the Intel AVX 2.0 instruction set, the Haswell new instructions, which include this fuse, multiply, and add command for vectors, for instance, 4 doubles at a time or 8 floats at a time. In addition, the per core P-states mentioned at the top here on power management allow cores that are not used to really be dropped almost down to 0 in terms of the amount of power that they use. And then in addition to uncore frequency scaling, we have a much more energy efficient turbo option. And we've also brought the voltage regulator online, or on socket for the Haswell processors. So Xeon Phi was released in January of 2013, and we are now planning and releasing some details about the successor to that, known as Night's Landing. And for instance, the goal is to be 3+ teraflops peak in one package. Some of the key things is it's going to be offering some 16 gigabytes of on-package memory, and this on-package memory has 5 times the bandwidth versus DDR4. So if you have problems, for instance, that fit in 8 gig or 16 gig, they'll be able to run without going out to the main memory of the system. In addition, there's 5x power efficiency improvements, as 3x single thread improvement compared to Knight's Corner. And the main thing is that all prior Intel executables for other architectures will be able to run unchanged on Night's Landing. The key thing that you will still have to make changes to your code in order to take advantage of the vector units in the architecture. So a recompile will be needed for optimal performance, but all executables are planned to run directly on that new system. So I decided that in order to really understand what I'm saying, I put some historical numbers together, for instance, that go back to 2009 up through 2014, and you see that, for instance, the R peak factor, which you multiply times the number of cores and the frequency in order to get the peak gigaflops, that is steadily increasing. The nominal frequency has tended to go down just slightly on the Xeon line, but the core count keeps increasing. So the R peak gigaflops column there, or row shown in green, shows a steady increase in compute capacity. And so if on the next slide, I just plot out the basic idea here, is that if everything is vectorized, the blue line shows the increase in performance from year to year, from 2009 to 2014. Now, if your code is not vectorized, then it would follow the red line. And then if most codes, for instance, are more of a mix, so the green line shows the relative set of improvement. But it's basically, the bottom line is that if you upgrade to Haswell now, this gives AVX2 capability, and it yields then MKL library can use those AVX2 instructions, and you get an application performance boost without MSC having to change any of their software. So now, if you keep the vector units really busy all the time, not like a matrix multiplication is a relatively low bandwidth requirements, but most applications require more bandwidth than say, a regular DGEM operation, then the memory bandwidth becomes critical. So memory bandwidth has been improved on Haswell. This shows the difference between Ivytown and Haswell. Now, Haswell actually can operate in 3 different BIOS modes. One's called Home Snoop, NUMA Home Snoop, NUMA Early Snoop, and then NUMA Cluster on Die. You don't need to worry about the differences there. It's just that if you want to tweak a system for optimum performance for a given code or workload, there are BIOS settings that can give you an extra, say, 3% performance differential in the new Haswell platform. And then, of course, in order to, if you want to try not to use your main memory as much as possible, you want to use your L1 and L2 caches as much as possible when you write software. So, and Haswell, in order to support these vector instructions and all the fuse, multiply, and add, etc., now has a doubled L1 and L2 cache bandwidth, and this is indicated in the diagram shown here. So as you change your block size, the gigabytes per second goes down because you end up operating out of cache. And finally, I'd like to, in the hardware department, just mention that, for instance, with a Lanczos solver, for instance, like MSC NashGen solution type 103, you can get in situations where if you're running out of core, you're using a lot of disk bandwidth. We have a new product called the SSD DCP 3700 series. You can look it up online. It's a shipping product. And just as an example of the type of change in performance, we show here a four-way SAS RAID 0 versus a single SSD versus a two-way RAID 0 versus a four-way RAID 0 versus this PCIe SSD card. And these are coming in different form factors in the future, so there's new types of disconnectors so that you'll be able to plug these things in to a regular backplane on newer systems and be able to get the type of performance shown here. So now just a quick wrap up on some software features is that, for instance, I mentioned our compilers, the Parallel Studio XE Cluster Edition provides you all the tools that you could possibly need when working with the Intel architecture. And in particular, MKL provides parallel direct sparse solvers, and there's this 4 clusters version now also, and you'll hear from MSC about their test with the Pardeso library. If you work with MKL a lot and you want to know particular features about that, you can activate a verbose mode inside of BLAS or LAPACK. We've also improved our small matrix size performance for single complex, double precision complex, and double precision gem operation. Our website is improving, and we have some cookbook recipes for different types of MKL features and optimizations. And one thing that's an example of what I referred to earlier is that Intel has announced its Advanced Vector Extension 512 or AVX 512 instruction set, and those actually have support in the latest version of the compiler as well as the latest version of MKL. So any codes linked with that will provide the appropriate speed up on those new architectures whenever they're shipped in the future. So I'll just wrap up with a list of URLs here that may be of use to you, and I'll turn it back over to Travis. Thank you very much.
Thank you, Paul. And thank you, everyone else, for joining us today. In this part of the presentation, I will be spending some time discussing improvements in performance to MSC software products based on the new Intel hardware that Paul has talked about, as well as the new Intel software. As Stephanie mentioned at the beginning of this talk, MSC has a long and productive relationship with Intel. We have several MSC teams working closely with Intel on performance, as well as relying on Intel to provide targeted training for products such as vTune and Parallel Studio when it is needed. The overview of this part of the presentation is as follows. First, I will discuss the performance benefit from upgrading to new hardware, as well as upgrading to new versions of our products, in particular MSC Nastran. Next, I will spend some time discussing the use of the MKL Partizo sparse direct solver at MSC Software and the new plans for 2014 and 2015 releases related to the Partizo solver. Note that there are 2 versions of the Partizo solver. Paul had mentioned earlier the cluster version. Today's talk will not be about the cluster version. That's for future work at MSC. I will end this part of the presentation by discussing our ongoing work with Intel on releasing a version of MSC Nastran with Intel Phi support. MSC Software has a large suite of products, with our newest being Apex, our computational parts-based CAE system. Today I will discuss mainly MSC Nastran, but also some new updates to our acoustic solver Actron from our FFT team in Belgium and our advanced nonlinear solver Mark. All of these products have similar requirements to get good performance. Each builds up a global matrix and then performs a matrix factorization. The matrix factorization can be the dominant cost of the overall simulations for many cases. These matrices can be symmetric or unsymmetric and real or complex. At MSC, we're constantly reevaluating the requirements of our sparse direct solvers with respect to new hardware in order to maintain our competitiveness. We have multiple teams evaluating new solvers from Intel, for example, the cluster Partizo, as well as ways to take advantage of today's mini-core architecture. As mentioned earlier, we will later show some of our joint work on support for the Xeon Phi and future releases of MSC Nastran. Next, though, we consider how hardware trends are impacting our work at MSC Software. As was stated in a 2005 article from a prominent C++ expert, the free lunch is over. The free lunch is, of course, the improvements in software performance due to increased processor speed. Today, we have to understand the hardware trends that were recognized in 2005 and are illustrated in this graph, which is that modern software has to take advantage of the increased core counts on today's CPUs to get speed up. As you can see, starting in the mid-2000s, clock speed, which is in dark blue, started tapering off, but transistors related to core count started to grow. This, of course, was clearly illustrated in Paul's part of the presentation, and is a critical part of the work that we do here at MSC Software to make sure we are constantly on the cutting edge. In the next slide, we will look at how MSC Nastran today benefits from improved Intel hardware with increased core count going from the Westmere released in 2010 to Haswell released in 2014. Here we have two types of simulations. On the left is a Dytran job or solution 700, and on the right is an advanced nonlinear job or solution 400. Dytran is an explicit dynamics code for simulating short duration events, whereas the advanced nonlinear solver is an implicit dynamics code. Due to Dytran's explicit nature, it scales very well with increased core count and can thus take advantage of new architectures such as that going from Westmere to Haswell, which can provide a 46% performance improvement. So what you see here on the left is going from Westmere to Sandy Bridge to Ivy Bridge to Haswell. We get an additional performance improvement just by going to a newer hardware family. The same is true also for nonlinear, where only we have data for Ivy Bridge and Haswell. In this slide, we just focus on performance improvements in going from Westmere to Ivy Bridge since we don't have data yet for the Haswell. But the trends are clear. On the left, we have a normal modes job where a user can expect a 49% improvement in performance from going to the newest Ivy Bridge hardware that we have on this graph. You can see that for a user that has a Westmere, upgrading to the Ivy Bridge, and of course if we had the Haswell, we would even see an additional benefit. We get a significant reduction in overall performance time. On the right, we have a fatigue job, and we again see the same trend in going from Westmere to Ivy Bridge. And we would expect that when we get the data for the Haswell, the trend will continue. So this is just, again, reinforcing the comment from Paul that you can get performance benefit with MSC Nastran just by upgrading to the newest hardware. So of course, it is not just about hardware, it's also about software. So what can we get with performance improvements out of newer software, in particular, newer versions of MSC Nastran? In this slide, we consider versions of Nastran that rely on the older MKL 10.3 library, you see this in the chart at the bottom, versus the new MKL 11.1 library. And Paul had pointed out some of the differences between the older versions of MKL and the newer versions. The key difference, as was pointed out previously, between the two versions is that MKL 10.3 only uses the AVX instruction set, whereas MKL 11.1 uses the AVX2 instruction set, as well as the 256-bit vectorization. One key advantage that was pointed out a few times of the new AVX2 instruction set is that it has diffuse and multiply add, which can, of course, provide additional performance benefit for those parts of the simulation where there's additions and multiplications going on simultaneously within, for example, matrix calculations or matrix vector calculations. The results for a series of problems from MSC Nastran shows that a 10% performance improvement can be obtained just by moving to a new version of Nastran that relies on the new MKL 11.1 library. What we have here at the bottom in this graph is, going from left to right, a medium-sized frequency response problem showing a 24% performance improvement. We have a large normal modes job, which is the second one. The third one is a large statics job, and the final one is a large normal modes job. Both of these normal modes jobs use the Lanczos solver to determine the modes for these problems. These are not ACMS, just the Lanczos solver. In general, MSC Nastran 2014, which uses the MKL 11.1 library and will be released in the next few months, gives 10% performance benefit just because of the newer version of the MKL library. This is something that we've seen throughout releases for MSC Nastran, that newer versions of this library gives immediate benefit to the customer. Now I want to shift from general hardware and general software to specific usage of the Intel MKL Pardeso solver. In many of our products, as stated previously, the matrix factorization can dominate the overall solution time. Furthermore, if our products are to effectively take advantage of today's multi-core architecture, then we know that the matrix factorization must itself effectively use many cores. The question is, what is the Pardeso solver? As described in the bullets, Pardeso is a sparse stretch solver in the MKL package from Intel that has good scalability in SMP mode. Note my emphasis on the SMP mode because this is the original Pardeso solver from MKL. Pardeso has just released a cluster version of Pardeso that has good scalability in DNP and SMP mode or over on a cluster. What we are releasing this year with MSC Nastran and with Actron, and what we have used in the past with Mark, is the SMP version of the Pardeso solver. Pardeso supports a variety of matrix types and can be used in core and out of core. It has parallelization over the number of right-hand sides. And in particular for MSC Nastran, it shows very good scalability in SMP and much better scalability for many problems than our default solver. Pardeso has actually been used in MSC's Advanced Nonlinear Solver Mark since 2008. And now in 2014, with the next release of MSC Nastran, and also with the next Actron release, which actually just came out, Actron 15, we will have two more products at MSC that can use Pardeso to provide improved scalability on today's multi-core architectures. So in the next set of slides, I want to show the performance that we have seen in Mark, in Actron, and in MSC Nastran. This will give you an idea of what we gain at MSC Software by using this part of the MKL library. We have been showing customers with our Mark solver for many years the scalability that can be achieved with Pardeso. In this slide on the left, we see the speed up that can be obtained for various problem size. These different colors are for different problem size, and the x-axis corresponds to the number of processors, and the y-axis corresponds to the speed up. As you can see, going out to 8 processors, the speed up can be anywhere from 3.5 to approximately 5.25, depending on the type of model and on the number of degrees of freedom. Of course, hypothetically, the best speed up is 8, but this corresponds to perfect scalability. For matrix factorizations, a speed up of approximately 4 for these problems represents 50% parallel efficiency, which is actually pretty good. The key thing is, if you look at the performance gain in going from 6 processors to 8 processors, you can see it pays off in increasing the number of cores that you use in your matrix factorization. This tells the customer that if you use 4 cores or 6 cores or 8 cores, you're going to get the lowest time at 8 cores. This is not always the case with a parallel code, which has a tough time achieving scalability. But for Pardeso in Mark, as you see here, it is advantageous to go all the way up to 8 processors. Now on the right, we can see that Pardeso is faster than the default Mark solver, BCS, and actually comparable to the very fast iterative solver, Cassie, in Mark, which is in green. So this shows the customer that you can use a sparse direct solver and get similar performance to an iterative solver for this problem. Let's move next to the acoustic solver, Actron, from our suite of products. Actron is the acoustic solver from our FFT team in Belgium. The sparse direct solver used in Actron has been the open source MUMPS solver that you see in these 4 charts. In the Actron 15 release just announced, the Partizo solver is added as an option, and these plots show the benefits. For Actron, one of the largest benefits actually is the reduced memory footprint for the 32-bit and 64-bit versions of Partizo. The top 2 graphs, labeled 1 and 3, show the performance improvement in time, in minutes actually, with respect to factorization for an unsymmetric matrix with increased core count, or in this chart, corresponding to threads. So you can see that Partizo, the 32-bit and the 64-bit version for the problem labeled 1, has very similar performance to MUMPS. For the problem labeled 3, MUMPS is a little faster, but if you look at the charts at the bottom, labeled 2 and 4, we see a significant reduction in memory used by Partizo in 32-bit and 64-bit mode as compared to MUMPS. This, of course, is very important for an Actron customer that has a limited amount of memory, that they can use Partizo to get that better performance and at a reduced memory footprint. Now we move on to the MSC Nastran 2014 release, which will be coming out in the next few months. So we will be providing, with the 2014 release, Partizo as a solver for advanced nonlinear, or Solution 400, as well as for linear statics with generalized linear contact, or Solution 101 with generalized linear contact. To specify the Partizo solver for Solution 400, you must specify the sparse solver in the executive command section of the bulk data file. Here is the pattern in the second bullet, and this can also be found in the quick reference guide, or QRG, as well as in the release notes for the upcoming release. The third bullet shows how you can specify the number of threads to use with Partizo. You can specify the number of threads with the parallel option on the command line, or the SMP option. I should note that we are moving away from the parallel option, so it is recommended in the future to always specify the number of threads with SMP. Next, we want to show some new performance results from the Partizo solver for Solution 400 to show the MSC Nastran user what one can expect with this new release that's coming out this year. In this first example, we have a 2.5 million degree of freedom solid element model from a customer in the auto industry. It is not using advanced nonlinear elements, as we specify in the third bullet. That means the overall wall clock time is dominated actually by the matrix factorization. Advanced nonlinear elements in Solution 400 require a higher computational cost, and so by Amdahl's law, the factorization isn't as dominant as it would be for advanced nonlinear elements. The results on the left show the scalability of the matrix solve time using Partizo, as well as our default solver called MSC LDL. MSC LDL is what you get in Solution 400 without specifying any solver with the sparse solver command. At 8 cores, we have a speed of approximately 6, implying a greater than 50% parallel efficiency for Partizo. Furthermore, we can see that at 16 cores, we are over 3 times faster with Partizo than our existing solver. This is on the left for just the matrix factorization. On the right, we see the normalized total simulation wall clock time. And what we see here is that we get about a factor of 2.5x performance improvement by using Partizo. Of course, again, Amdahl's law says that The factorization is not the only thing going on within the simulation. There are other aspects of the simulation. So we don't get the 3x performance improvement, but we get about a 2.5x. As we see at the bottom, Partizo is especially effective on these large solid element models. The next example is another one from a customer in the auto industry. This is 3.5 million degrees of freedom, and it is a shell element model or a car body. We're using the same machine as previously, but here we're using advanced nonlinear elements, which are a little bit more expensive. And so again, by Amdahl's law, the factorization time isn't as dominant. So if you look at the left, what we see is the performance benefit in going from 1 to 16 cores for the matrix factorization only. You can see in this example, MSC is a little bit faster for serial, but by 16 cores, the factorization is about 2 times faster for Pardeso. We don't see the 50% parallel efficiency, but we do see a very good parallel efficiency, and you can see what the user can expect for performance benefit from using Pardeso. On the right, this is the overall normalized total simulation wall clock time for using Pardeso and for using MSC LDL from 1 to 16 cores. The overall reduction in wall clock time is only about 20% instead of a factor of 2.5x as in their previous slide, which was solid element model and no advanced nonlinear elements. So a couple things to point out here is shell element models, or these car body models, the matrices are less dense, meaning you do not get the parallel efficiency that you do with solid element models, which have very dense matrices. So that's why these performance numbers are different than for the previous slide for the solid element model. In the final example of performance, we show Partizo performance for a model that is essentially a linear statics job or solution 101. As the fourth bullet point shows, there are no advanced elements and no contact, and it's just essentially one matrix solve. This is a machine with 60 cores and 2 terabytes of memory. It's a very large machine that we had a customer work with us on these numbers for. Again, it's a solid element model, and it's an engine part. Over 15 million degrees of freedom and over 10 million elements. On the left, it's the same figure as for the previous slides. It is the matrix factorization time and the scalability going from 1 to 60 cores. At 30 cores, we have 50% parallel efficiency for the Partizo solver, and in particular is 3 times faster to use Partizo than MSC LDL for SMP only here. It's very impressive. The overall performance improvement is about 2x at 30 cores when using the Partizo solver. So again, this is a solution for 100 job with no advanced elements and no contact. And this is what we are releasing in 2014. I will show later our plans for the 2015 release, which is to of course support Solution 101 as well as many other solution sequences. But this is what one can expect in the 2015 release for a Solution 101 job. Here are some very interesting numbers. With the help of the Intel team, we have also explored just the factorization time and FPS time for a matrix from a Nastran simulation for a variety of architectures. So in this case, we were able to pull out the matrix from Nastran and provide it to the Intel team and let them test performance on Sandy Bridge, Ivy Bridge, and Haswell to give you an idea of the performance differences between these different architectures. As can be seen in this graph, going from Sandy Bridge to Haswell delivers a 33% performance improvement in factorization time, and this would, of course, be directly translated to a Nastran simulation. It depends on whether you're using advanced nonlinear elements in Solution 400 or whether you're using contact in terms of overall benefit. But for just the factorization, here you see a 33% benefit going from Sandy Bridge to Haswell when using Pardeso. Also, just going from Ivy Bridge to Haswell shows a 14% performance improvement. The story is the same, and that's that to get the best performance from Nastran, you really should upgrade your version of Nastran and upgrade your version of hardware to the most recent Intel hardware. There are some important notes here. Sorry, the slide has gotten a little bit off-centered here. I'll explain what we see, though. First, we should note that the existing MSC LDL solver and MSC Nastran has been designed over many years to work with a minimal amount of memory. Again, MSC LDL is the default solver in MSC Nastran. Only parts of the matrix are brought in core when the factorization is done. This reduces the peak memory requirement. You can see for this problem, so what we have here hidden is that we have a part of the F04 file from an MSC Nastran run using MSC LDL and Partizo. So for this example, MSC LDL only requires 12,641 K words or 48 gigabytes of memory to run the factorization part of this simulation. This is in I4 mode. Pardeso requires 618 megabytes of memory, so it's a significant amount of difference. But the MSC LDL solver was designed at a time when memory was very limited. Pardeso, though, will get the best performance when it can fit in core, and so the memory requirement is a little higher. It's 736 megabytes of memory. But our belief is that customers have the memory today. We have many customers that are running with 256 gigabytes on a node, or some are even soon going up to 512 gigabytes. And so that's going to give you the best performance for these simulations, to give enough memory to Partizo. In MSC Nastran, we cannot only think of solver memory or open core if you're familiar with the F04 file, but we also have to think about buffer pool or buff pool memory. Buff pool is memory used by MSC Nastran to buffer the I.O. Since Nastran was designed to work with minimal memory so that you can solve large problems with less memory, there is a significant amount of I.O. when running a typical simulation, especially if you do not have enough memory for buff pool. The more buff pool memory that you specify, the lower will be the I.O. costs. With Partizo, there's going to be some competition with where memory should go. The user should reference the F04 file to see how much available working memory there is and how much is needed to be in core for Partizo. In this example above, we have 3,200 megabytes of memory available for addition to the buff pool. So you can't see it, but the available working memory for Partizo is actually 4,591 megabytes, but we only really need 1,344 megabytes to be in core. That leaves an additional amount of memory that can be used for buff pool. The final thing I want to note is that we can actually combine DMP and SMP in Solution 400 with Partizo. The way it will work is that DMP will speed up the nonlinear element matrix generation. This is already available in Solution 400. But when you use DMP with SMP, what we will do is we will take the 8 threads that are used by Nastran and use them with Partizo. We believe that it's best to use all threads possible to get the best performance, and so that's how it's used in Solution 400 with DMP. Before we end today's presentation, we only have a few more slides to go. I want to discuss some ongoing work that is tentatively planned for 2015. MSC Nastran has been working closely with the Intel team on providing support for the Xeon Phi in the 2015 release. We are currently targeting Solution 103, 108, and 111, with an alpha release tentatively planned for early to mid-2015. The chart in the bottom shows some of our ongoing work. It shows the peak performance for dense matrix-matrix calculations, or DGEMs, that are at the heart of our default sparse direct solver MSC LDL. During the factorization, there are many DGEMs performed, and we block them up into smaller matrices to get best performance. The graph shows the performance with respect to various matrix sizes. To date, best performance is to ensure square-sized matrices in our DGEMs. So again, to note, the release for 2015 that will be supporting the Xeon Phi is to provide acceleration for MSC LDL. And there will be an alpha, and customers will be made aware of this alpha whenever it is available. In summary, I want to say you will get the best performance if you purchase the newest hardware from Intel, and of course you will get the best performance if you upgrade to the newest version of MSC Nastran. Again, the release that will be coming out in the next few months has the new Partizo capability for Solution 400, as well as Solution 101 with Contact. and it uses MKL 11.1, which provides the AVX2 instruction set. We will be extending the support of MKL Pardeso for the 2015 release, as well as completing our work on the Intel Xeon Phi. And finally, longer term, we will be exploring the use of the Intel Cluster Partizo version, both for the Actron product, the MARC product, and the MSC Nastran product.